Do you know what a combinational logic design is? Well, let's delve into it together. Combinational logic design is a cornerstone of digital logic. It finds its implementation in Boolean circuits, which are the building blocks of digital computing systems. The fascinating aspect of combinational logic is that its output is purely a function of the current inputs. It doesn't concern itself with past inputs or outputs, making it a truly in-the-moment system. This type of logic design is everywhere around us, from the simple calculators we use every day to the complex computer systems that drive our world. So why should we learn about it? Because understanding the principles of combinational logic design can help us to not only comprehend, but also create the digital world we are part of. In this video, we will walk you through a step-by-step process of designing a combinational logic circuit. So let's get started. The first step in designing a combinational logic circuit is to define the problem. So let's familiarize ourselves with the problem at hand. We aim to design a 2 to 4 decoder, a type of combinational circuit. But what exactly is a 2 to 4 decoder? Well, it's a circuit that takes a 2-bit binary input and activates one of 4 outputs based on that input. In simpler terms, we're creating a system with 2 inputs and 4 outputs. The 2 inputs can be any combination of zeros and ones, and depending on the input, one of the 4 outputs will be activated. The inputs are often labeled as A1 and A0, and the outputs as Y0, Y1, Y2, and Y3. Our task is to design this decoder in such a way that it correctly maps the inputs to the right outputs. Now that we have defined our problem, we can move on to the next step. The second step is to create a truth table that represents the relationship between the input and output values. Now, what is a truth table, you might wonder? Simply put, a truth table is a mathematical table used in logic, specifically in connection with Boolean algebra, Boolean functions, and propositional calculus, to compute the functional values of logical expressions on each of their functional arguments. In the context of our current task, which is designing a 2 to 4 decoder, the truth table will show us how the binary input values correspond to the output values. The binary input in this case is a 2-bit value, represented as A1 and A0. This means there are 4 possible input combinations, 0, 0, 0, 1, 1, 0, and 1, 1. Now let's focus on the output values. We've got 4 outputs, denoted as Y0, Y1, Y2, and Y3. Each of these outputs will be activated based on the input binary value. For instance, when the input is 0, 0, Y0 will be activated. When the input is 0, 1, Y1 will be activated, and so on. So, our truth table for the 2 to 4 decoder will look like this. When A1 and A0 are both 0, Y0 is activated, and the rest of the outputs are not. When a 1 is 0 and a 0 is 1, Y1 is activated, and the others are not. If A1 is 1 and a 0 is 0, Y2 turns on. And finally, when both A1 and A0 are 1, Y3 is the one that gets activated. What our truth table does is visually represent this input-output relationship, making it easier to understand and follow. It's a neat and organized way to showcase how the inputs relate to the outputs, providing a clear map that will guide us through the rest of our combinational logic design process. With our truth table complete, we can now proceed to the next step. Remember, each step in this process builds on the previous one, so understanding the truth table is crucial before moving forward. The third step involves writing Boolean equations for each output based on the truth table. This step is crucial as it represents the actual logic of our circuit. To write these equations, we will use something called minterm notation. A minterm is a specific combination of inputs that results in a high output. It can be represented by a product of literals where each input variable appears exactly once. In our case, we have 2 input variables, A1 and A0. For each output, we will write an equation that represents the condition under which that output is high. Let's start with Y0. From our truth table, we see that Y0 is high when both A1 and A0 are low. This can be written as the minterm A1 asterisk A0, where A1 and A0 represent the complements of A1 and A0. Next, we have Y1. Y1 is high when A1 is low and A0 is high. This can be written as the minterm A1 asterisk A0. Moving on to Y2, we see that this output is high when A1 is high and A0 is low. This translates to the minterm A1 asterisk A0. Finally, we have y3. y3 is high when both a1 and a0 are high. This is represented by the minterm a1 asterisk a0. So we have our Boolean equations as follows. y0 equals sign a1 asterisk a0, y1 equals sign a1 a0, y3 equals sign a1 asterisk a0. These equations directly represent the logic that our circuit needs to implement. They are the key to transforming our problem from a conceptual one to a practical one. Remember, writing Boolean equations accurately is essential, as any mistakes here will be carried forward into our circuit design. Now that we have our Boolean equations, we can move on to the next step. The fourth step is to implement the circuit using logic gates. Now, if you're new to digital logic design, you might be wondering, what are logic gates? Well, they're fundamental building blocks of digital circuits, used to perform basic logical functions that are fundamental in digital circuits. The three basic types are AND, OR, and NOT gates. Let's dive in deeper. An AND gate is a digital logic gate with an inputs and one output that performs logical conjunction based on the combinations of its inputs. The output of this gate is true only when all the inputs are true. On the other hand, an OR gate is a digital logic gate with an inputs and one output that performs logical disjunction. The output is true if at least one of the inputs is true. A NOT gate, also known as an inverter, is a digital logic gate with one input and one output that inverts the logic state. If the input is true, then the output is false, and vice versa. Now that we understand what logic gates are, let's use them to implement our Boolean equations. Remember those equations we derived for the outputs y0, y1, y2, and y3. We're going to implement them using AND, OR, and NOT gates. For instance, to implement the equation for y0, which is a1 bar and a 0 bar, we will use an AND gate with the inverted inputs a1 and a0. Similarly, for y1, which is a1 bar and a 0, we will use an AND gate with the inverted input a1 and the normal input a0. We follow the same process for y2 and y3. So, there you have it. We've implemented our 2 to 4 decoder using logic gates based on the Boolean equations we wrote earlier. It's not too complicated when you break it down into these steps, right? With our circuit implemented, we can move on to the final step. The final step in designing a combinational logic circuit is to verify the functionality of the circuit. Now that we've implemented our 2 to 4 decoder circuit using logic gates, it's time to make sure everything works as expected. This is where our truth table, created at the beginning of the process, comes back into play. To verify the functionality of our circuit, we'll use the truth table and a simulation. In essence, we're checking to make sure that for all possible input combinations, our circuit produces the correct outputs. Picture this. We start with the input combination of 0 and 0. According to our truth table, this should activate output y0 and leave all others inactive. We input these values into our simulation and voila! Output y0 is active and all others are inactive. That's a tick for our first input combination. Next, we move on to the input combination of 0 and 1. Our truth table tells us that this should activate output y1. We run the simulation again and there we have it. Output y1 is active and all others are inactive. That's another point for our circuit. We repeat this process for the remaining input combinations, diligently checking off each one against our truth table. If all goes well, our circuit operates just as we designed it to, and we can confidently say that our 2 to 4 decoder is functioning correctly. However, if we find that our simulation does not match our truth table for any input combination, then we have an error in our circuit. In such a case, we would need to go back to our Boolean equations and logic gate implementation, find the error, correct it, and then verify the functionality of the circuit again. This verification process is incredibly important, as it ensures that our circuit works correctly before we use it in a real-world application. That concludes our step-by-step guide to designing a combinational logic circuit. Let's quickly recap what we've covered in this video. We've journeyed through a practical example of combinational logic design in digital logic design, designing a 2 to 4 decoder. We started by defining our problem, needing a circuit that can take a 2-bit binary input and activate one of 4 outputs accordingly. We then created a truth table to define the relationship between our inputs and outputs. This was followed by writing Boolean equations for each output based on our truth table. Remember to use min-term notation. Next, we implemented our circuit using logic gates, specifically AND, OR, and NOT gates. Finally, we verified our circuit's functionality using our truth table and simulation to ensure it produced the correct outputs for all possible input combinations. Remember, practice is key in mastering combinational logic design. Keep practicing, and soon you'll be designing your own circuits with ease.